Before moving into vectors, I just want to talk about generally moving from 2 dimensions to 3 dimensions. Okay? We're used to working on a Cartesian plane. It's 2-dimensional. We have an x-axis, we have a y-axis. And we have this one coordinate plane and we break it up into 4 quadrants named like so. We start where everything's positive and move around anti-clockwise our 4 quadrants. Any point has a unique position, the ordered pair, the x value, the y value. Now we move into 3 dimensions. It's no longer a plane, it's now a space. So we move into this Cartesian space and we add in a 3rd axis, the z-axis. You don't have to draw it in this orientation, but it seems to be the standard way of doing it, where you put the xy plane flat and the z one's coming through it, and the x one you'll see is pointing towards us. We now have 8 octants and 3 different coordinate planes. So originally we just had one plane. Now we've got 3 of them. We've got the YZ plane, the XZ plane and the XY plane. The octants, how they're named, the first octant, similar to the Cartesian plane, everything's positive. Then we move around and do more like we did with this one. So 1, 2, 3, 4, so it's still the same 4 quadrants if you like. But then we flip and go the other side of the plane, now the Z. So we're basically flipping on the Z. So the first one, when Z's positive, go around the 4 quadrants like before. Then you go when Z's negative and go around again. That's how we name it. But the point now is named with 3 pieces of information. So X, Y and Z. Problem is, our piece of paper is 2-dimensional, so to represent that, that's really hard to get a feel for where P actually is. So often we might draw in a rectangular prism like that, and then that gives us a feel for where it's actually sitting, in which octant and so on. Without that, as I say, it's a bit hard to work out. So what do we know in 2 dimensions? We know we have lines parallel to the coordinate axes, and so parallel to the x-axis would be y equals a constant. Parallel to the y-axis would be x equals a constant. Basically, the one that it's parallel to sort of disappears out of the equation, if you think of it that way. The reason I can think of it that way is because now, if we look at planes that are parallel to the coordinate plane, so it will be z equals a constant, is the one that's parallel to the xy plane. So it's like the x and the y have dropped out. So I've just got z equals a constant. So it would come through like that. It's parallel to the one that I've placed flat. If it was parallel to the xz plane, then it'll be y is equal to a constant. So it'll come down like so. And then if it's parallel to the yz plane, x would equal some constant. So it would come through down that way. A couple of our very common formulas that we work with in coordinate geometry. Distance and midpoint. Distance formula in 2 dimensions we know is this. Well, what happens in 3 dimensions? If I now grab 2 points sitting in 3 dimensions, I want to find the distance between those points. Okay, again, I'll just draw a rectangular prism so I can get a feel for it. What we're really saying is, what's the length of the diagonal of that prism? Okay, well, I could draw up a right angled triangle like so, and we could find the length z2 minus z1. If I was to just project the base down onto the xy plane, it might make it a bit easier to see, well, hang on, I know they're the difference in the y values, they're the difference in the x values. The hypotenuse of that one becomes the square root of x2 minus x1 squared plus y2 minus y1 squared, because essentially we're just saying what's the distance between these 2 points in 2 dimensions. There's our distance formula, but hang on, we can tidy that up because the square root squared, and what we see, basically it's the same thing. And this is what we find. When we push it through to another dimension, the formula generally stays the same. We've just pushed it through to another dimension, so we add a variable in. So now, in our square root, we've added the distance between the z values squared. And the midpoint formula, in 2 dimensions we know it's that, it's the average of it all. And guess what? Yeah, sure, in the 3 dimensions, again, we just push it through to the 3rd dimension. We're now averaging the z values as well. So everything transfers over very nicely.